Welcome everyone, and thank you for joining us today for our webinar titled Microneurography, Recording Nerve Traffic via Intraneural Microelectrodes in Awake Human Subjects. This is Andy Henton from Inside Scientific, and it is my pleasure to be your host for today's event. Our session is brought to us by AD Instruments and will focus on using microneurography as an invasive technique to study nerve activity and associated responses in human subjects. The presentation will be led by Vaughan Macefield, Professor of Physiology at Mohammed Bin Rashid University in Dubai and Professor of Integrative Physiology at Western Sydney University. Dr. Macefield is known internationally as a world expert in recording the firing properties of human sympathetic neurons in health and disease and as a leading investigator in human sensomotor control. For over 10 years, Vaughan has been examining the changes in control of the autonomic nervous system following human spinal cord injury, extending his research into the study of pain and its effect on the autonomic and somatic nervous systems, using brain imaging techniques such as fMRI to study the processing of pain. Professor Macefield was also a leading consultant regarding the development of the NeuroAmp X extracellular amplifier, which he will be showcasing today. Today's presentation will be a brief introduction to microneurography technique and an overview of the associated equipment and methods for recording nerve response. Following a selection of applications will be discussed to highlight common research applications and approach, and then we're going to have a Q&A session with Dr. Macefield focused on the methods and application of microneurography, as we've had a number of questions come in during the registration session.
Welcome everybody. I'm Vaughan Macefield. I'm going to be talking about microneurography and specifically the use of LabChart and AD Instruments NeuroAmp X for recording from peripheral nerves in awake human subjects. So as most of you are aware, microneurography, which has been around for almost 50 years, was developed by Karl-Erik Hagbarth and Åke Valbo in Sweden, and it's contributed significant information on tactile and proprioceptive sensation, pain, sensory motor control, and control of the sympathetic nervous system. Tungsten microelectrodes can be inserted into any accessible peripheral nerve, usually the median or ulnar nerves at the wrist and or the upper arm, and these are useful for recording from tactile afferents and spindle afferents, etc. The common peroneal or tibial nerves at the knee, and these are typically used for recording from sympathetic activity. Interestingly, the Japanese favor the tibial nerve at the knee. Recordings have also been made at the sural nerve at the ankle, and in recent studies we've been recording from the posterior tibial nerve at the ankle, which allows us to record from muscle spindle endings in the intrinsic muscles of the foot and cutaneous afferents in the sole of the foot during standing. So that's an interesting area of our current research. Microelectrodes can also be inserted into branches of cranial nerves, so they're not limited to just peripheral nerves. So recordings have been made from the inferior alveolar nerve or the supraorbital branches of the trigeminal nerve. And my colleague Mats Trulsson in Stockholm in Sweden, he made the first recordings. He's a dentist by training, and he made the first recordings from the inferior alveolar nerve in the open mouth, and this is the nerve that is blocked by a local anesthetic when you go for your lovely visits to the dentist. So as I mentioned, I'll be talking about the NeuroAmp X. Many of you will be using, if you're currently performing microneurography, you'll be used to the Iowa system, the Iowa amplifier, which is based on the original amplifier developed in Uppsala by Karl-Erik Hagbarth and his colleagues. And this is the same amplifier that I trained on, David Burke in Sydney. The NeuroAmp X is a new type of amplifier, and I was involved as a consultant providing the system specs and testing all the prototypes, and it is a very good low noise amplifier. As you can see here, it's got a wide band pass, 100 Hz to 5 kHz, and importantly a high signal to noise ratio. The head stage, which you can see here, this stainless steel cylinder and cable, Provides preamplification, gain of 100, and it also has a high-pass filter of 10 Hertz. The cable shielding is directly connected to the casing, and this limits the need for additional shielding at the input terminals. So the input terminals shown here are very high impedance, and importantly they have input protection circuitry. So if you are like me and you use intraneural stimulation through the microelectrode, you can attach a small mini alligator clip directly to the terminal of the active electrode and deliver currents up to 1 milliamp without fear of damaging the circuitry. As you can see, the NeuroAmp X is safe for direct human connection, making it ideal for microneurography. But also the shape allows it to be used for animal research, so it was designed with this also in mind because it can fit into, for instance, a Narashiki micromanipulator. And in my earlier days, I was doing animal work, so I know that this sort of amplifier would be ideal for extracellular recordings from individual neurons in the brain, or even from peripheral nerves in anesthetized animals. Anyway, as I mentioned, this is ideal for use in microneurography, and this just shows how we would attach it to the leg of a subject. Shown here, you can use a Velcro strap to wrap it around the leg, around the calf, or as shown here, you can just tape it on. You don't need to put gel on the head stage, and in fact you shouldn't put gel on the head stage because that could, enter the terminals and short circuit or even damage it. So don't put any gel here. What you can see in the green lead is attached, well, you can't see it, but it's attached to a simple silver chloride surface electrode, just a stick-on ECG electrode over the knee or anywhere. There are two electrode points, two electrode terminals. Let me just go back here. You can see here. So we have a ground lead is attached here, and this is a differential amplifier. So one of the inputs is positive, the other is negative. We have a microelectrode inserted into the common perineal nerve, shown in this inset here. The blue mark simply indicates the site over the nerve that is defined as the best site for inserting the nerve. And we do that by, sometimes you can palpate the nerve, but often, well, always, we will use surface stimulation through a 1 to 2 millimeter surface probe. We deliver cathodal currents, 2 to 10 milliamps. And when we're over the nerve, then of course we're getting twitches of the innervated muscles and or paresthesiae, pins, needles in the innervation territories of cutaneous fascicles. So we then mark the site, insert a microelectrode, the active recording microelectrode into that site and into the skin about 1 centimeter away, the inactive or reference electrode. These are commercially purchased microelectrodes. We get ours from Frederick Hare. You can buy specific microneurography needles, they call them. These will typically have this wire attached and a little tape flag. I don't like the little flags because they tend to slide down. So I just purchased them with the gold male amphenol connector shown here. And I just make this little connecting wire out of copper winding wire. It's insulated. You need to scrape off the insulation with the last 1 or 2 millimeters and solder it to the pins that come with the amplifier. So the amplifier head stage comes with 3 male and 3 female pins, and you can order additional ones from Frederick Hare or WPI. Typically we will use a microelectrode that has gone through several cycles of use. Once its impedance becomes very low, we just use it as a reference electrode. We will scrape about 1 millimeter off the tip. clean it and re-sterilize it. Now, some of you, your human ethics committees or institutional review boards may not allow microelectrodes to be reused, re-sterilized, which I think is crazy. In which case you can buy reference electrodes, so just bare reference electrodes from FHC. So this is a schematic of a peripheral nerve. As you'll be aware, it's composed of distinct fascicles. The level of the knee, for instance, some will supply tibialis anterior muscles, some extensor digitorum longus muscles, some will supply cutaneous fascicles. Here we have a representative recording, an extracellular recording from a single muscle spindle ending in tibialis anterior. It is firing spontaneously. These are positive going spikes. This is what we'd expect from a monopolar recording from a myelinated axon, in which the microelectrode tip has got very close to and is indeed penetrated the myelin sheath of the axon. Spontaneously active discharge, which we have increased by applying stretch to the receptor bearing muscle. So just by passive plantar flexion of the ankle will stretch the tibialis anterior muscle and activate, will increase the firing of this spindle primary ending. In the lower recording, this is multi-unit activity from a bunch of C fibers, specifically the unmyelinated axons supplying blood vessels in the innervated skeletal muscle. So this is muscle sympathetic nerve activity, which is vasoconstrictor in function. As you can see, it has a very strong coupling to the ECG, so it exhibits strong cardiac rhythmicity. So this is a typical recording obtained in my lab using the NeuroAmp amplifier, and I hope I can convince you that the noise is very, very low indeed. I've used many amplifiers over the years. I've been doing micronography for some 30 years. And often you would need to apply a bit of aluminium foil over the head stage just to block out any electrical interference. The NeuroAmp X, however, does not require shielding. It is a very, very low noise amplifier, and you can see here that the peak-to-peak noise is 8 microvolts. If we look at the root mean square process, this is a root mean square moving average with a time constant of 200 milliseconds, you can see that the noise level is below 2 microvolts. And it is very hard to get lower than this because the background noise pretty much reflects the thermal electrical noise of the amplifier itself. So it's hard to get below this. So conclusion here is it's a very low noise amplifier. And this is an oligo-unitary recording, so you can see the firing of individual sympathetic axons, but we can see groups of axons firing here with a clear cardiac rhythmicity. Using the amplifier, we can also, as I mentioned, record from myelinated axons. These are generating positive going spikes, unlike the negative going spikes of the sympathetic axons shown here. Positive going spikes here recorded from a Golgi tendon organ afferent in tibialis anterior. Here we've got surface EMG recorded with the BioAmp, one of the front ends from that connects to the power lab, and this is the root mean square, the RMS processed mean voltage, so the mean activity of the EMG. In the lower trace we're recording dorsiflexion force, and we have a little target shown here, and the subject is instructed to dorsiflex the ankle against the strain gauge and reach this target force, which you can see he does adequately, and on the right we can see that once he reaches the target force, the Golgi tendon organ maintains a constant firing rate. Now we can use the window discriminator software in spike histogram, which is some software that one can apply to the lab chart recorder data to extract the firing of this single unit. I'll come back to this. I'll demonstrate this later. Interestingly, and I'll also come back to this, you can see that within this recording you can see spontaneous bursts of muscle sympathetic nerve activity. So sometimes we get this, and it can, you know, for a recording where we're interested in the activity of the myelinated afferent, this sort of activity can be a bit of a nuisance, but you'll see sometimes it can be beneficial. This is a recording I made in a microneurography workshop that I ran in Telluride, Colorado last year. This is not an ideal laboratory situation. We've got a power supply for this robotic manipulator here. We've got the microelectrode inserted into my median nerve at the wrist, a ground electrode on my arm, and here's the head stage. A reference electrode is just nearby. And basically what you can see, let me just kill the sound, what you can see here is the spikes being generated by this fast adapting type 1 afferent on the finger pad. You can see the little black mark there shown here, and we've got a very good signal to noise ratio here. And as I said, this is not an ideal laboratory situation. This is just in a schoolroom, despite which we've got very, very nice recording indeed. So using the NeuroAmpX, as I mentioned, we can get very crisp recordings from single myelinated axons. This is a slowly adapting type 2 ending, a Ruffini ending in the finger pad, and here we're just applying a compressive force to the finger pad in each of these positions and superimposing a rotational or torque force. And this just shows a screenshot from the window discriminated spike histogram discriminator, where we can put a cluster, put windows around this cluster of spikes. We can see the individual spikes on the right. This is in the Macintosh version. I'm used to the Mac, but I should say that the Windows version has much better functionality. It has template matching, which is very, very useful. And so you can remove spikes or insert spikes directly. So it's a very, very powerful software. So I actually went to the headquarters of AD Instruments in Dunedin and worked with the software engineers there to get that functionality built in. Unfortunately, it's not fully fully applied to the Macintosh version yet, but nevertheless, as you can see here in the Mac version, that is still very much adequate for extracting very clean spikes from a recording. Many of you will be interested in muscle sympathetic nerve activity, and I'll show this example just because this subject displayed very nice and spontaneous fluctuations in arterial pressure recorded with the phonometer. And you can see that when there are spontaneous falls in blood pressure, there is a compensatory increase in muscle sympathetic nerve activity, an increase in muscle vasoconstrictor drive, which drives up blood pressure, and then through the arterial barrier reflex, of course, inhibits this activity. It also causes a compensatory increase in heart rate. So using the NeuroAmpX, we can, and using the spike discriminator software, we can extract the negative going spikes, and I'll come back to why we do this. But here, what I've done is extracted the negative going spikes from this multi-unit recording of muscle sympathetic nerve activity. Here you can see the RMS processed nerve, so you can see these bursts and you could count these bursts. But here, what I've done is displayed standard pulses, so unit events of the spikes being generated in this multi-unit recording. Down here, I've used the same software to extract the R waves of the ECG, shown here, and in the lowest trace, I've used the same software to extract the positive peaks of the respiratory record. So we have events of muscle sympathetic nerve activity, all the spikes being generated, the R waves for the ECG, and the inspiratory peaks of the respiratory record. Now, you may ask why we are interested in getting that. Well, it gives you another way of analyzing muscle sympathetic nerve activity, or skin sympathetic nerve activity for that matter. Here you can just record that, you can just measure the burst frequency and burst incidence. You could measure the amplitudes, but by getting the spike timing of the sympathetic nerve activity and the event timing of the ECG R waves and the inspiratory peaks, we can generate autocorrelation histograms and cross-correlation histograms. So we can look at the timing of the sympathetic spikes as a function of the timing of the R waves and as a function of the timing of the inspiratory peaks. And this is shown here. If we look on the right panel, just in panel D, time 0 here for all panels represents the time at which the event occurs. So here, this is the first R wave, and this on the right shows the timing of the subsequent R wave and the following R waves to the right and the preceding R waves to the left. Now, if this was a patient with a pacemaker, this would be very tight. These peaks would be very tight, but because this is a healthy individual, then there is some variability, normal heart rate variability, and we can see this in the broad peaks of the spike timing. This is just shown to illustrate the basic cardiac rhythm in this individual, but on the top what we've done is generated a cross-correlation histogram between the MSNA and the ECG, and you can see that the dominant peak corresponds to that which would be most closely coupled to the R wave, 1.5 heartbeats previously, about 1.2, 1.3 seconds previously. So this just shows the marked cardiac rhythmicity of muscle sympathetic nerve activity. We can go in and we can measure the total number of spike counts there. So this is another way of quantifying muscle sympathetic nerve activity, not from the RMS processed or integrated nerve, but from the raw nerve signal itself. Likewise, on here we've got the autocorrelation histogram of the respiration, the inspiratory peaks, time 0 and the next, the breath afterwards and the one after that and preceding. And again, this shows that this signal has very nice respiratory modulation as well as cardiac modulation, though of course the cardiac modulation is greater. And we can see the same thing with skin sympathetic nerve activity as well. Now, I mentioned that occasionally we will get recordings in which we have muscle sympathetic nerve activity infiltrating an afferent recording. Depending on where your area of interest lies, you may find the muscle afferent to be an inconvenience, or you may find the muscle sympathetic recording to be an inconvenience. For me, I think it's great when we get recordings like this because you can actually get 2 recordings for the price of 1. I'll actually come back to this particular example in the software demonstration. We'll go through it in detail. Suffice to say that here I've extracted the sympathetic spikes, the negative going spikes, and the positive going spikes, and the peaks of this sinusoidal galvanic vestibular stimulation. This comes from some work we've been doing over the last few years where we're applying a weak electrical current behind the ears, and it induces strong vestibular illusions of rocking in a boat or swinging in a hammock. And basically, again, using the cross-correlation histogram and autocorrelation histogram functions of spike histogram, we can look at the modulation of muscle sympathetic nerve activity as a function of this vestibular input. We've previously shown that it doesn't have any effect on the spindles, but it does cause marked modulation of muscle sympathetic nerve activity here. As you can see, for 3 different frequencies at 0.08 Hertz, 0.13 Hertz and 0.18 Hertz. And we also see this modulation when we're recording skin sympathetic nerve activity. So again, by performing cross-correlation analyses, you can get very rich data from a multi-unit recording. So there's more in the signal than is obtained just by simply recording the number of, or measuring the number of bursts per 100 heartbeats or per minute. Now, many of you will also be aware that using very high impedance microelectrodes, we can record from single sympathetic axons. This is technically very difficult, of course, because the axons tend to travel in a fascicle as a group. So the idea is to get the electrode tip as close as possible to one axon in which the generated spike stands out from the noise. And here we've got a muscle vasoconstrictor neuron just firing spontaneously, and we've got the asterisks indicate when the unit is firing, and here in the inset we've just superimposed the spikes, and you can see that this has a uniform spike morphology. We can also see far field activity, and here in the integrated nerve, which is similar to the RMS process nerve, we can see this far field activity, so we can get an idea of the population activity as well as the single unit activity. We can see what happens when we ask the subject to increase the muscle sympathetic nerve activity during a physiological maneuver such as a maximum inspiratory breath hold. And this is why you can see the respiration is flat here. Subjects have been asked to take a maximum inspiratory breath hold, an inspiratory capacity apnea, which causes a sustained and marked increase in muscle sympathetic nerve activity. Again, we can see this great increase in activity from the integrated nerve. The far field activity being picked up by the same microelectrode gives us an idea of what the population of neurons is doing. But by having the microelectrode tip close to one axon, closer to one axon than the other axons, we can see that these spikes, which stick out from the background and are superimposed here, give us an idea of what individual neurons are doing. And as you can see, individual neurons, and this is a common feature we have found, are generally firing once and only once per cardiac interval. Occasionally they fire 2 to 3 times, 4 times within a cardiac interval. We can look at different disease states. So I've looked at obstructive sleep apnea, hypertension and heart failure. Elizabeth Lambert at the Baker Institute in Melbourne, she's done a lot of work on different disease states, including panic disorder and obesity and hypertension. And basically the pattern is very uniform across labs. Individual neurons tend to fire once per burst, but as you can see, they can occasionally fire multiple times, although this is rare. Now, at the outset I mentioned that the head stage of the NeuroAmp X is made of high-grade stainless steel, and this is actually advantageous because we were thinking, oh, maybe we can use this in the scanner, because we'd been doing some brain imaging work and we were interested in identifying sources of the brain responsible for generating bursts of muscle sympathetic nerve activity or bursts of skin sympathetic nerve activity. And like most people at the time, we'd been using physiological maneuvers in the scanner that we could also use in the lab. So we'd get recordings of the physiological changes in the lab, including what muscle sympathetic nerve activity or skin sympathetic nerve activity is doing. And then in the same subjects, we'd put them in the MRI machine and scan the brain and use the same maneuver. We asked the question, well, would it be possible to record the sympathetic outflow at the same time as scanning the brain? And basically we managed to do that. So, and the idea here is that by correlating bursts of muscle sympathetic nerve activity or skin sympathetic nerve activity with brain activity, we could identify regions in the brain responsible for generation of this activity. And we've looked at patients with sleep apnea as well, and we're currently looking at patients with hypertension. So MSNA coupled fMRI or SSNA coupled fMRI allows us to identify these regions of the brain that are temporally coupled to the bursts of MSNA or SSNA. If you imagine the bursts that we're recording from the microelectrode in the peripheral nerve, you imagine these bursts as like flashes of a lighthouse beacon. And you imagine that there are many lighthouse beacons flashing in the brain. By recording the two signals together, we can see which of the lighthouse beacons are flashing together and therefore which of the areas are temporally coupled. So this shows a recording from a sleep apnea patient about to go in the scanner. We have the neuroamp attached to the leg, exactly, everything's the same, there's no shielding here. This is the head coil, 32-channel head coil, and this is a 3T scanner. We've also been doing this in Nottingham using a 7T scanner. We are planning to do the same in the 7T facility in Melbourne. Anyway, this was the very first recording we took, and we thought that we would there'd be a lot of noise, and so what we did is we thought, well, should we put a bit of aluminium foil over? Well, we didn't bother, but this was the first recording. We've got scanning artifacts here, and we've got a lot of noise here. We were really worried about all this noise, but then, like good neurophysiologists, we thought, well, maybe we can filter that out. So this is now the same recording with a high-pass filter, 300 Hertz high-pass filter. I'll just go back. Got all this noise down here, but you can make out a burst there, and when we filter it, you can actually make out two bursts. So simple high-pass filtering applied offline. So we now apply this routinely. So as soon as the recording finishes, 300 Hertz a high-pass filter kicks in and removes the overall background noise. We can then use this feature called peak parameters. We can highlight a burst. We can measure its amplitude, its width, its area, anything we want. We can measure. And what we've been doing is we've been using a 4-second on, 4-second off scanning period. We record this 200 times. Basically, this takes advantage of the delays inherent in blood oxygen level dependent signal in the brain. So basically, an electrical event in the brain, a neural event, is followed about 5 seconds later by the blood oxygen level dependent increase in signal intensity. Because neurons, when they're active, they require more oxygen, which is delivered by the blood, and because blood contains hemoglobin, which carries the oxygen, of course, and hemoglobin contains iron. It has a paramagnetic quality. I won't go into the physics of it. Suffice to say that there is a signal, a bold signal, that is used as a proxy marker of neural activity in the brain. We also know that it takes about a second for that neural event in the brain to travel to the peripheral recording site at the knee, because these are slowly conducting axons, and it takes about a second to travel from the brain down to the recording site. So 5 seconds for the bold signal minus 1 second for the nerve conduction signal leaves us with 4 seconds. So what we've done here is we just measure the burst activity in every 1 second epoch in this 4 second off period where we can actually see the nerve activity, and jump ahead in time to the brain scanning and look within the brain at the bold signal that is occurring 4 seconds after the 1 second period of interest. I shan't go into the details here. Suffice to say that when we use this approach, we can see areas that are temporally coupled to the bursts of muscle sympathetic nerve activity, such as ventromedial hypothalamus, dorsomedial hypothalamus, cingulate, precuneus, and we can see in these cross-sections again these areas of the hypothalamus, torsomedial and ventromedial hypothalamus. We can also see deep cerebellar nuclei, the anterior insula, etc. So these are areas, dorsolateral prefrontal cortex. These are areas that just pop out from the analysis. There's no region of interest here. So these are just temporally coupled to the spontaneous burst of MSNA. Therefore, they are likely to be contributing to the bursts of muscle sympathetic nerve activity.
I'm going to start with can you record nerve activity from multiple sites simultaneously?
Yeah, you can. I mean, of course, you need 2 amplifiers, but we often record from the left nerve and the right nerve. So we have 2 neuroamps, and they work very well. Obviously you just have to get into 2 nerves, and that takes a bit longer. You could also record from the same nerve, so at a distal and a more proximal site. This would be trickier getting into if you want to get into the same fascicle, but it's definitely doable, and there's no issue with respect to compatibility between the recordings from two neuroamp amplifiers recorded at the same time. Yeah.
Perfect. Okay. And then this leads us into our next question, because I'm sure there's maybe additional challenges if you go to recording multiple sites. But a number of questions have come in. How does one determine the proper location of the needle to ensure consistent and accurate measurements?
Yeah, so one thing you should be aware of is that when recording muscle sympathetic nerve activity, for instance, the amplitude of the signal depends on the proximity of the electrode tip to the active axons. Now, you can't just get one subject and record from that nerve, a week or 2 later. Well, we usually wait 4 weeks before entering the same nerve. You can't record and expect that amplitude to be a consistent representation over time, because, as I mentioned, the amplitude depends on how close the electrode tip is to the active axons. However, many people will normalize the burst to the largest burst recorded in that recording session. So if you call that 1000, say, the largest burst you've recorded, and normalize everything to that, then you can look at the distribution of amplitudes from one session to another. But this is why most people are interested in just a very rudimentary but powerful means of assessing sympathetic outflow, which is simply to record the number of bursts per 100 heartbeats, burst incidence, or the number of bursts per minute, burst frequency. Now, using single unit recordings, which is of course trickier because you have to make very, very fine adjustments of the microelectrode tip, so you get close to one and only one axon. The nature of that signal is quantal, What I mean by that is that you've either got a spike or you haven't. And so with that approach, you can just record, you can compare the signal from one subject to another, because what you're interested in is the firing probability of a neuron, how many times per cardiac interval does it fire, etc., and the frequency. So using the single unit approach, you can compare recordings between individuals, but using a multi-unit recording, it's much more difficult to use anything other than temporal measurements, that is burst frequency or burst incidence.
Perfect. No, that's a very good answer. Perhaps on this topic of, again, training or just learning the fundamental skills, what suggestions do you have, Vaughan, for people that are new to microneurography and want to start?
Oh, look, I think that's a very good question. Look, you know, microneurography has been around for 50 years now. There are many people in the world doing it, but it's still a technique that is very specialist. It is not something you can just try at home. You need to be trained by a proficient microneurographer. In my lab, I take students every year, and it takes me, a couple of months to train them. But they'll still need to be making the recordings under supervision. It takes quite a while to become proficient. It's not an impossible technique to learn. It requires you to, one, experience it as a subject, and two, to be trained into inserting and manipulating a microelectrode into a nerve, because you're inserting, this is an invasive procedure. It's very safe, but it is potentially unsafe in unskilled hands. So you need to identify an investigator who uses it and ask for training.